In this video, we will be covering how we created our character controller. Before we start, it's recommended that you watch the previous video on the camera controller. Though it may not be necessary, this video builds on top of that one and the result shares both the input and the camera controller script. However, if you have your own camera controller, feel free to use it. If not, you can find our camera controller in the description below. So we know how to control the camera around the character, but what about moving the character itself? Functionality of character controllers have generally been the same, especially for third-person games. For instance, third-person character controllers usually apply their input based on the camera. If the character is facing towards the camera and the player inputs forward, the character would turn around instead of moving in the direction that they're facing. Some games have it so the character always turns towards the direction that they're moving in, while others would allow the character to walk backwards. And that's just the start of it. There's ground detection, crouching, jumping, sprinting, collision detection, terrain detection, directional movement, swimming, climbing, air state, strafing, sprinting, jumping, attack. But before we go over all those features, we will start by covering our basic character controller. So with all that said, let's get started. We'll start by replacing our stand-in cube for a character model. The one here is a free model from Mixamo, as well as the animations that I'm going to be using. To keep the project organized, I'll create a models folder and animation folder. The animations that I'm using are fast run, idle, standard run, and walking. Here you can see the model in the preview window in the bottom right. We'll modify some of the import settings. In the model tab, under the scene heading, uncheck both import light and import camera. In the rig tab, change the animation type to humanoid and avatar definition to create from this model. If you choose to use your own model, you'll have to ensure that it's configured properly. Apply the changes. In the animation tab, uncheck the import animation and apply that too. Similar to our model, we'll have to modify the import settings of each of the animations. Starting with fast run, uncheck import light and import camera just like before. Change the avatar type to humanoid, but this time we will select copy from other avatar as our avatar definition. Since the animation shares the same rigging of our model, we can set the source to the avatar we created from that model. Make sure to apply the changes. In the animation tab, we'll check the loop time option. Since this is an animation that will continuously play, this will allow the animation to loop. We'll change the root transform rotation to be based on the original. These settings will matter more in cases where you rely on the root motion created by the animator, the person, and not the calculated motion. But in our case, we'll be moving the character without it. Root transform position Y will be based on feet, and root transform position XZ will be based on original. We'll bake into pose for the root transform rotation and the root transform position Y. Baking removes the root motion, meaning the game object will remain in place but the mesh will still move. Apply the changes and do the exact same thing for all the other animations. Drag the model into the scene and add both the comp player inputs and comp camera controller script to the model. Go to the cube and copy the settings of the scripts and paste them into the components on the new player, and delete the cube when you're finished. If the model doesn't already have an animator, then add that to your model, and be sure the avatar matches the one you created from before. In the project, create a new folder for animator controllers, and create a new animator controller for our player. In the animator controller, we'll create a new blend tree called Base. Double-click to enter the tree. Here, we'll change the blend type to 1D and create a float parameter called Forward. Now change the blend tree to be based off the forward parameter, then add all the animations under the motion box in order of idle, walking, standard run, fast run. Uncheck automated threshold and manually change each threshold to be 0, 2, 6, and 8 respectively. Now we can preview how the blend tree looks. Notice how changing the forward slider moves the blend tree between the animations. By blending the animations together, we can create a smooth transition between the different states of motion. Back in our scene, we'll add this new controller to our model under the animator component. We'll create a new C# script named comp character controller and begin scripting. Surround the class with your existing namespace, and as always, get rid of the start and update functions. For this script, we'll need references to our other components. As such, we will need to create the following. Create a private animator variable called animator. Create a private comp player inputs variable called inputs, and create a private comp camera controller variable called camera controller. Recreate the start function, and we will assign each of these references by using getComponent. Ensure that the type that you're assigning matches each of their corresponding variable types. We will also ensure that the animator root motion is false. This can also be done inside the inspector, but I prefer this. Before going any further, we'll need to make some changes to our other scripts. We'll start by opening our comp player input script and define what our input actually is. Outside of the class, but in the namespace, we'll create another public class called input to handle this. We'll use two public key codes, one for our primary key and a second for our alternate key. We'll then create three public Boolean functions to get the state of our inputs using Unity's getKey. The first will handle our pressed input state, returning true if either the primary or alternate key code is currently pressed. The second, called pressed down, will return true only on the frame that they are pressed down. The last, called pressed up, will do the same as pressed down, but for the pressed up state, only returning true during the frame where the key state goes from pressed down to pressed up. To end it off, we'll serialize this class so that the editor can display it. Inside the player inputs class, we'll declare inputs for our character. We'll create a forward, backward, right, left, and sprint input. Along with those inputs, I'll create an integer property called moveAxisForwardRaw. If forward is pressed, it will return a value of 1. If backwards is pressed, it will return a value of -1. If both or neither are pressed, it will return 0. Next, we'll do the same for another integer property called moveAxisRightRaw, where right is positive and left is negative. Additionally, the character controller needs to know where the camera is facing, and instead of calculating it, we can get the value from our camera controller script. In the camera controller, we'll add a vector3 property called camera planar direction, and it will return the private planar direction. This way, any script that wants to access this value can call this property. Returning back to our character controller, we can bring back the update function. We'll create a local vector3 called moveInputVector. It will be a new vector3 where x is equal to the moveAxisRightRaw, and the y is equal to 0, and the z is equal to moveAxisForwardRaw. We'll create another local vector3 called camera planar direction and retrieve the property that we created earlier inside the camera controller. We'll create a quaternion called camera planar rotation, which will be the rotation based on the camera planar direction. We'll pass the camera planar direction into quaternion.lookRotation to convert the vector into a quaternion. And I'll use a debug to see if the inputs are working correctly. Before we test this though, I'll create a new game object with the character named CameraFollowPoint. Raise it by 1.5 and assign it to the follow transform of the camera controller. This will make it so the camera won't be pointing at the player's feet, or wherever the origin is. This can also be done by adjusting the framing. For the sake of the test, I'll hide the floor so we can see the results of our input. Test every direction and ensure that they are correct. You'll notice that the diagonal inputs are longer than the others. In order to prevent the player from moving quicker when moving diagonally, we'll normalize our input value. Currently, the move input vector is relative to the world, which our player happened to be aligned, but we want it to be in relation to our camera. To do this, we'll set the move input vector to be a product of itself and the camera planar rotation. I'll create another debug ray to visualize this new direction. Upon testing, we can see that when we want to move forward, the red line shows the movement vector is aligned with the camera forward. Ensure this is true for all the other inputs. So now we have to calculate the speed at which the player moves. To do this, we'll need to create some more variables. Create a header called movement, and our first serialized variable will be called run speed. I'll assign it the value of the threshold of the run animation in the blend tree that we created earlier, 6. Then we'll create two more private variables, target speed and new velocity. In the update function, we'll check if there's an input by evaluating the move input vector. If there isn't an input, target speed will be assigned 0, otherwise it'll be our run speed. From there, we can calculate our new velocity by multiplying the move input vector with the target speed. To apply this to our character, we'll take the character transform and translate it by our new velocity. To make this translation time dependent rather than frame dependent, we'll multiply this velocity by time.delta time, converting the velocity to be units per second rather than units per frame, which is far faster as dozens of frames can occur in 1 second. Lastly, we'll set space relative to world rather than self. Back in our scene, we can test and see if the movement is correct, as the player's movement corresponds with our inputs. Next, we need to handle the rotation. I'll create a private quaternion called target rotation. I'll only update the rotation when there is input, because I don't want the player to rotate back to the quaternion identity when there is no input. Since target speed already checks for input, we can use it for our condition. If the target speed is not equal to 0, our target rotation is the look rotation of our move input vector, and then we can apply that rotation to the character. Back in the scene, we can see the character rotating to face the target direction. Now we want to see our character actually running as they move. To do that, we'll call the animator and use the setFloat function and set the parameter forward to be equal to the target speed. When testing this, the start and stop is abrupt. That's due to the speed not ramping up, but rather jumping from idle at 0 and running at 6. Before fixing this issue, we'll quickly implement sprinting, as well as declaring several variables. Similar to the run speed, we'll create a variable called sprint speed and assign it a value of 8, the same as a sprint threshold in the blend tree. We'll also create a private float called new speed and a private quaternion called new rotation. Then I'll make another header called sharpness with a private float called rotation sharpness and a private float called move sharpness. Inside our update function, we'll check if the sprint input is pressed. If it is, then we'll check if there is a move input. If there is, then target speed is set to 8. If not, then we'll set it to 0. We'll move our previous target speed assignment into the else condition. To smoothen the new speed, we'll utilize mathf.lit to move between itself towards the target speed. The interpolation between the two will be based on delta time multiplied by the sharpness of the movement. Then replace the target speed in the new velocity line with this new speed variable. We'll now do the same for our rotation, using quaternion.slurp to spherically interpolate from our current rotation towards the target rotation. Again, the interpolation value will be the product of delta time and the sharpness, and we'll assign new rotation to the player's rotation. Lastly, animator.setFloat will use the new speed rather than the target speed. Don't forget to set the move and rotation sharpness to values alike. I have mine both set to 10. Before we test this, I'll add a capsule collider and a rigid body to have collisions in gravity. This isn't the best method, but it's quick. For the capsule, I'll change the center y-axis to 0.9, radius to 0.25, and the height to be 1.8. For the rigid body, I'll constrain the rotation on the x and z axis. This will make it so physics won't ever topple the character and they will always remain upright. You can now test the project and see that it is working properly, and there you have it. It's not perfect, but it's a good start. I hope you enjoyed this video and that you took something away from it. If you have any suggestions as what we should do next with our controller, feel free to leave a comment below. For now, we'll leave it here and work on various other projects. Anyways, thanks for listening and I'll see you next time.